Hey, Tiago.
Hey, hey, can you hear me?
Yeah.
Yeah. Okay. Outstanding.
I don't know if Rosemary's coming in today. I emailed her.
Okay.
I'll let you know.
Just, mute me and kill me.
Yeah.
I don't have a problem with that.
Yeah. The talk doesn't start till 10 past or something, quarter past.
Ah,
So
okay.
go and have
Okay,
a
okay.
coffee, Tiago.
Okay. Yeah, I'll be here at my desk. No worries.
Okay.
I'll
See you later.
see you later. Thank you, Phil.
Is he on? Yeah. Ready for that?
I am on.
Oh, hello.
Hello, hello.
How are you?
I'm good. I'm good.
Can you see me? Or
No, I can only see the screen. Yeah, now I can see.
this is so nice. But is there a way I can like look at you and look at you?
Yeah, you have to look like so. There you go. There you go. Almost.
Hey,
How are you doing?
Steven, how are you?
I'm good. I'm good. Actually, I was just talking about you yesterday
Oh, that's
because
sweet.
because I had the first meeting with this woman in Mexico that's going to be Madalena, my student's co-supervisor.
Yeah.
And she was really very interested in trying to see if someone might be interested in playing with her what seems to be an outstanding capture-recapture data set for these whale sharks. And so I was again mentioning your name. And I think, if you're still looking for something that might be an interesting topic, maybe this could actually be a really interesting data set to explore different things.
Yeah.
I'm going to talk to Len on Friday for a little bit, but my suggestion is that we could all meet at some point just so I introduce you guys, and then, if you guys think it's interesting, feel free to take it on, and if not, well, feel free to not take it on, I
Yeah.
guess.
Oh, that sounds really amazing. I know that there's also going to be a new PhD position from September.
Okay.
For someone who's going to focus solely on whale sharks.
In St. Andrews?
Yeah, it's a new PhD. I think they're looking for someone right now.
I had no idea about this.
But they're going to focus on, I think, the Maldives.
Okay.
Because they have a lot of different data there, so there's a whole pile of citizen science and everything combined. And that's what they're looking at.
Will you, if you happen to find it, I don't know if you received an email or something, but will you send me a link to this? Because I guess, given that
I think it's going to be supervised by Hannah.
Okay.
I talked with her and Len about it.
Okay. Well, that's nice to know. I mean, it's interesting to see so many people working on sharks. So maybe people can learn from each other. That sounds cool. Anyway, I will let you know what transpires from that, and maybe then I can introduce you to those folks if you and Len think it's useful. They seem they seem good from the biological point of view, and I think they need help with the methods. You guys, you're good with the methodological point of view, and interesting data sets probably give you good research questions to be explored based on those. So I think everyone has something to gain there.
Okay, awesome. Wait,
okay.
I'm not curious. Wait, you're seeing yourself on the screen.
Yeah, it's an infinite
Is it kind of like a process that goes on forever, or not?
Yeah, it's kind of a bit.
See yourself on the screen.
Yeah, yeah, and I think if the universe hasn't exploded by now, it won't anymore.
Okay, we're now joined by 3 others as well.
Okay, I'll catch you later, Felix.
And Fanny is here.
Aha.
Yes, I'll send you the slides now.
Thank you, Fanny. You're a star. I'll mute myself just to avoid me, sneezing, snoring. No, I'm not snoring, given it's Fanny, but sneezing.
Hey, Fanny, how you doing?
Hi.
All right,
Good.
Tiago. Let me know how Friday goes.
Okay, see ya.
Thanks. Hi, Tiago. Rosemary's arrived, so I'll switch you off later on.
Very well. Okay.
Okay, I've just sent them, so let me know if they don't arrive.
Thank you, Fanny. I'll just check.
Can I use my own laptop?
Yeah, just go back over here. We've got the right connector, see which ones we need. Which ones we need. What have you got on this?
I always use that one to connect to my own screen. I also have this.
That's done, yeah.
Oh no.
Hundreds of times.
How much took your box? The one outside the office.
Yes, yeah. It's actually too big to do anything.
Yeah, because I have to move lots of stuff, but it's even, I mean, for books it just gets too heavy.
Yeah, well, if you try to put the book, you'll never lift it.
Yeah.
Hi, Fanny. Just to let you know, stuff is here. Thank you very much.
Oh, fantastic.
Okay. And yeah, so hopefully, there we go. Hopefully I'm not flickering. Do you want this?
Yes.
Now it's been safety checked. You have to dump the other one because there's a danger.
To what, cats or?
Yeah. I don't know, if you fire at somebody's eyes, you could blame what happens.
I mean, usually a trying point is the slide. But, yeah.
No, but I think it's a good idea to keep people on their toes. There we go. Okay, I'll switch you off, Tiago.
Okay, Phil.
Okay,
I'll mute myself in any case.
Look at this shirt that I found.
It looks really nice.
Looks like I'm a normal person.
I was literally about to say from the
No,
start, you can
no,
barely see
no,
it,
yes,
you're like,
statistician.
that's very nice, like, presenter outfit.
It's also, I realized this is a shirt that's going to fit 3 months.
Yeah. This is actually true. You can. It's only if you lean now. You can see that you lean your hand on it, like if you.
It also sometimes it gets stuck like this.
Very obvious. Yeah.
It's big enough. Well, I'm changed now.
Yes. No, it's this. Yeah.
Ah, easy.
Yeah. That's
Source
a good,
is just
that's
about
a good
small
slide.
enough.
Can you do the next one, please? That looks amazing. The last one. Like these nice
That's my research.
nice straight lines, and then it just.
This is the only slide on my research, by the way, just so.
I like the styling done.
It's one of the like 10 PowerPoint things.
This is a really nice one. Like the
And also now I've discovered you can type LaTeX on PowerPoint.
yeah, I'm gonna steal this template.
Can you see that that's purple and not black?
It's like it's bluish. It's different for sure. Look at that narrow distribution.
Okay.
That's
I don't
a
know why I
good
put
fit.
that in.
That's a brilliant fit. Can you show that fit, please?
What?
Thanks for that. Oh.
Great now. It's not meant to fit. It's meant
Oh.
to, but it's meant to be flatter.
Oh, that was. No, it's because of the
I
image.
guess I changed something after.
No, the image.
Yeah, but usually I just copy and paste the slides and don't change like this kind of.
Yeah, but I've seen this before happen. It's weird. It readjusts things. This is actually quite. This is a cool plot.
I think I'm gonna hang those.
So you mean?
art in my.
I know I'm already asking, but these are like points that are removed and resampled because they were too far out. Okay, but this is such a.
Yeah, you can see that that one has the same. No, that's the important sequence. No, never mind.
Okay, I'm not going to ask you this question. Because I think you already said it.
See, no one's gonna read that line.
This is a very nice.
Here you go. I can also do math.
See, I did math before people actually
I
read
thought
it.
that like some technical conditions we can do this. No one can.
Yeah, unless you get language. Sorry, can you go back to slide number? Yeah.
What is
So,
it? I know
line-
what
line
the
two.
technical condition is.
Line 2, what does KT refer?
The red's not really that good, is it?
Is the sequential importance sampling red? It's supposed to be, it kind of comes, no, it does come out red, just very dark. This looks super clean, like a nice balance between text and images.
Yeah.
So you're done. Are you already with Epsana?
Huh? That was lucky. No, that's a research group that works on my stuff. And I went for a workshop.
When you went to that conference
Yeah, it's a workshop.
for the workshop, yeah. And this is the talk you got, huh?
I mean, it was a week-long workshop, and this is basically a condensation of that workshop.
Oh, okay.
Minus the stuff I thought was irrelevant, plus the stuff I think is right.
Okay. Oh, so it's not just your work, it's also...
That's good.
Okay, sorry. Now I do.
Because no one, I mean...
Yeah, that's my switch to wiggle. Probably not jacket. I don't know, you can never tell with this string. Sometimes it's old bowl.
Surprisingly warm.
Yeah.
The solo orbital launch, which was really cool. I've never seen one for multiple years.
See it in the back? See it in the back?
Yes. Okay, clever. was really. Sorry? Oh, it's amazing. We weren't that close, like 50 miles away on this beach. The amount of power that's going on. Kind of went close that off. That was supposed to, but it's share.
Oh, that's going to point to me. Yeah. Oh, no.
And I realized that it's by the beach.
You didn't have to watch it. We had 2 hours together on the beach.
Oh,
Right, I'm going to calm down, curb your enthusiasm somewhat. So it's my pleasure to introduce Fanny Empachers, who's been a PhD student with us for a few years, and is working on particle filtering. And so I kind of untwisted her. I think I untwisted you, or did you offer? I can't remember now. It was me. I untwisted her. I thought that these methods are very general and quite possibly widely applicable to things that various of us are doing. And so I guess I untwisted her into giving a tutorial, which has turned into 2 lectures. So this will be part 1, and part 2 is in a couple of weeks, I think. Yeah. Over to you, Fanny.
Right, well, thank you for coming. So I'm going to talk about sequential Monte Carlo methods today, which is a really sort of wide class of fitting methods. And today we'll talk about state inference a lot. So I'm funded by the EPSRC, which I didn't put on there. And lots of this work. So I went to a workshop in Uppsala in August, which where there's a research group who's working on this stuff from an engineering point of view. But it really turns out to be exactly the same kind of stuff they're working on. And that was very helpful, and so lots of stuff is kind of adapted from that workshop as well. So the aim today is to sort of introduce these methods and also give some idea of where it's going and what sort of tips and tricks are and what sort of the cool new stuff is. And I've split it up that today we're just talking about state inference, so we have some sort of latent state that we want to find out things about, and the next time I'll talk about parameter inference. And the reason for that is that we need to solve the state inference problem well enough to be able to start looking at parameters. So what's a state-space model? I assume most people know, but this is also to clarify my notation. So we have some sort of process. It's a time series with some sort of unknown hidden state that we can't observe, that's following some kind of process that we're interested in. Unfortunately, we can't really observe that process, so we have some observations y that are not exactly what we want to know, but they're related to what we want to know, and we know how. And then we also have some model parameters that we probably don't know. And really, all we need is these 4 equations to make the state-space model work, to define the model. So we need to know how does the observation relate to the state, how does the state evolve through time, and then we also need to know a little bit about the starting conditions and possibly about the prior. But there's no reason why this doesn't need to be in a Bayesian context. So it lends itself very well to a Bayesian framework because it's already hierarchical, but it doesn't need to be at all.
So is that the same P in each case?
Yes, sorry. So I should say that. So my notation is, I think, understandable but slightly sloppy in that I use P whenever I'm talking about any kind of model density. And the argument sort of, I always put the argument, and the arguments kind of make it clear which density exactly I'm talking about. And then whenever I use a different density, that will be Q. So Q is every bit.
Does the first line mean that yt is independent on past values of yt?
Yes. So,
Okay.
So we start as a graphical model. Exactly. So we see this graphical model that shows the conditional independence structure. So like Valentin said, given xt, yt is independent of all the other values. And then the same for the states, they're Markovian. So once we know xt minus 1, no previous information about state is going to help us with xt. So the state has the Marcus property, the observations only depend on the current state. And the time is discrete, but there's no reason why it can't be irregular, so we can, T doesn't have to be regular. And states and observations can be whatever. Okay. Right. So there's lots of examples where state-based models are useful. So this is my own research. In this case, I'm looking at the UK grey seal population. The states are just the age class, age structure of the seals in every year. So it's 7 different age classes. And the process is just sort of survival and birth, that's binomial. And the observation is that we can only see the tops, as you can see from this picture. So someone has to go and count the tops in this picture. So they're just observed with some normal error around them. A lot, so you can sort of, if you want to draw what the actual state, the process looks like, it's like this, and that I'm only including this to show how flexible these models are and that we can really chuck in lots of things. More examples in ecology, movement models are really common. So we have the true state will be the location or maybe the speed or acceleration or something, and then the observations of some kind of measurement from the tag, whatever that gives us. Then stochastic volatility models are sort of really typical state-space models examples. Please don't ask me anymore, but I don't know. But they do, there's very common examples for state-space models and kind of and then epidemiology, for example, we have SIR models, and then our observations might be the number of deaths or something like that. And then lots of other applications. Basically, anywhere we have a time series with some kind of observation. And I thought I might could just some sort of toy example for this. So it's really simple. It's not quite linear and Gaussian, but almost. So we just have sort of this kind of process with the black lines here in the pictures is the state process, and then the blue dots are my observations. And we're just I'm going to use this to show how the different algorithms work and what sort of the advantages and disadvantages are. Right. So what do we actually want to do? What state inference? We want to learn about the underlying state, maybe in some time frame, given the observations we've already made. And what we're pretending for now is that the parameter is known, so we'll just ignore theta from now for the rest of the talk. And there might be a few different questions that we want to know. So for example, we might be interested in the filtering distribution, and that means at my current time point, given everything I've seen up till now, what can I say about the underlying state? I might also want to make a prediction, so given everything I know up till now, what's going to happen next year or tomorrow? I might also be interested in the joint smoothing distribution, so I want to know the entire path, so how did the animal move, or what kind of shape did the population growth have, or whatever. Or I might just say, in that specific year, 10 years ago, given everything I know, even until now, what can I say about the state that happened a while ago? And I'm going to talk mostly about filtering today, and I'll touch a little bit about how smoothing works as well and what the problems with that are. And the rest kind of comes out of that as well. So, right. So what's the state filtering problem? So we want to learn about this distribution. So the first idea we could have, let's just write it down. What is it? So it did. And so there's nothing magical happening here. It's just a base rule, and then we're using the Markov property. That's the state-space model has. And then I'm looking at this term and just splitting that up further into things that I know about a little bit. So this is not as pretty as we'd like it to be, and we can't calculate it because it has this ugly integral, and then it has this kind of expression that we don't really know. The only nice thing that we notice is that these two purple things sort of seems like there might be some kind of iteration going on, and that's what we're going to exploit. So we're going to use, because we can't calculate anything, we're going to use Monte Carlo, and we can use Monte Carlo to to evaluate integrals of each type. So if we look back at this integral, we can interpret really either of those as the target density and the other thing as phi here. And yeah, that's a clever way to split it up. Yes?
Sorry, can I just interrupt? When you say that theta is known, you don't mean that you integrate out theta.
Yes. No.
So theta is known.
For now, yes.
So you actually, to do these integrations, you have to assume certain values, or yeah.
Yes.
Yeah.
For now.
Yeah.
The time I've actually seen that used in the real world, because usually theta isn't known, right? And that's, in 2 weeks' time, we'll talk about how to estimate it. But the classic state space problem that started this stuff in the 1950s was a missile ballistics problem. So you've got an incoming missile, and you know, because it's just ballistics, you know what the process underlying that trajectory would be, but you don't know where it is, and you've got measurements of an angle and a distance, and you want to know where it is in X, Y, Z, because you want to know where it's going to land or fire. So that would be a case where the theta is known.
Yeah, so in engineering generally that's more often the case, what we know.
Sorry, what's the function phi?
Oh, I didn't say, sorry. That's just some sort of target density. So we might want to know, so this is a density that we're interested in. So we might want to find out if we want to know the expected value of phi of x, if x is distributed according to the target density phi, and we can't evaluate this integral, then what do we do? Okay, so assuming we have a sample from pi of x, then we can just approximate this integral with this sum. So really simple, what is phi of x is just x, and we want to find out the expected value of something, the mean. Then we just sample from our target distribution, and we take the mean of all our samples. So that's the most intuitive way. And what we can see here, I've just estimated the mean of the uniform distribution, which is not very difficult, but it sort of shows that, first of all, our estimates are, the estimated mean is unbiased, and also the variance decreases when we increase the sample size. So that's the takeaway, I think, that higher sample size makes sense better. The problem is we usually, so of course now uniform distribution we can easily sample from the target density, but usually we can't do that. So what we can often do, for example in the state space model context, is we can evaluate, we can't sample from it, but we can evaluate. So once we have a value, we can say what's the density at that, sorry, that's a up to a constant. So for example, if we go back here, we have this sort of horrible constant, so we might be able to do something at the top here, but we can't really calculate this constant. So we might be able to evaluate this thing, but not the constant. So the thing that we can do then is importance sampling. So this is the algorithm. So basically sampling from some other distribution, can be almost anything. There are some restrictions, but we sample from any distribution, and we compute weights. So we have a sample that's from the wrong distribution, and then we computate weights that are really high if the sample fits very well to our target density. But so I will give the sample a value from the sample a really high weight if it matches the true distribution, the target density really well. And I also have to make up for the fact how likely it is that we sample this with the proposal distribution. And then we just have to make sure everything comes to 1. So that's a weighted sample that we then can kind of use to calculate an integral like this. So lots of math happening, but what we really have to do is we take a weighted mean instead of the normal mean. So we can do this cleverly or not so cleverly. For example, I'm trying to get a weighted sample from the uniform distribution, and I'm using the normal distribution, standard normal distribution as a proposal. And what we can see is it kind of works, but then here at the end, we get these really high weights, and it sort of gets uneven, and that's because the shapes are so different in that area of the normal distribution and the uniform distribution. And if we take a different proposal, so we shift it a bit over and take the better shape, then it's much smoother. So main takeaway from this, it's important what kind of proposal distribution you choose. So the slight problem with important sampling is that there's a bias that vanishes with n, but for any finite number of n, there's a bias. So, for example, if I do this, so I'm using the standard normal again as a proposal. I'm trying to estimate the mean of the uniform distribution. And I'm taking 50 samples, which is decent, but not really a lot. We can see that it's really, really biased. So it thinks the mean is somewhere here, and this is the true mean, of course. And I've also looked at what happens if we increase the sample size, so we get closer and closer to 2, which is the true value, but we always have that little bias. So that's also important to keep in mind, that we always, everything we do with importance sampling is biased. Okay, how can we use the importance sampling idea in a state space model? We're basically looking at what happens if we go from one time step to the next. And we're using that idea here. So this is the algorithm. So we're starting, I'm going to try and give sort of an intuitive explanation on the right here. So we're starting, we're sampling from some sort of initial distribution that we have to know. And because we sampled from the correct initial distribution, everyone gets the same weight.
Why are you just sampling powers?
Oh, sorry. That's so the subscript is the time index, and the superscript is the index within the sample. There's never.
It doesn't mean the power.
There's no power ever in this talk, so just to not have double subscripts. Right. So once we have that initial sample, we want to go one step forward, and what we're doing is we're sampling from this, so from our process density. So we're saying we know what the state was like at time x0. What do we think if we sample for each of the particles? So we call the we call the xi's, they're called particles. So for each of the n particles, we sample forward. So we're saying if it was this, if it was this value at time 0, where could it be at time 1? We're completely ignoring the observation we made at time 1 so far. And then we're giving it a weight, and the weight is how well does the observation match that state that we just projected forward to. So if it went off in the completely wrong direction and it can't really possibly have happened with that observation, then we give it a really low weight. And if it sits right on the dot where we think it should be, then it gets a high weight. And we do this sequentially, so the weights sort of get multiplied one after the other. So I've tried to sort of show this here. So we start by sampling from some initial distribution. Our particles would all equal weight. We go forward, we propagate to time 1. Then we look at, so this is meant to be sort of the observation density. We see which of the particles match really well, and they get a high weight, and the particles that don't match well get a very low weight. And then we go on. So all the particles get distributed again, and the weights that multiply each other. So this is a really nice idea, and what we get is an asymptotically unbiased sample from the filtering density. So this looks very nice, but there's a problem with it if we look at our type sample. So I've just run that here, and what you can see in this picture, so the blue line is the true state, and then I ran a particle filter with 100 particles, and so that's all the black lines here, and the black lines are stronger depending on how high the weight is. And what we can see here, sort of from time about 5, we can see that there's really only 2 or 3 lines that we can still see, and at the end there's really only this one line that's still dominating the picture. Which means at time 25, we now want a sample to estimate whatever you want to estimate, that basically consists of one particle, because all the other particles have tiny weight. And this is the histogram of the weight, so we can see that basically numerically 0, and then we have this one weight, one particle that's going to determine everything. And an effective sample size of 1 is not really helpful. So, how do we solve this? We're going to go to the first proper sequential Monte Carlo methods, which is the Switzer particle filter, and that's sort of the basis for everything else. So if you understand this, then everything else that comes out of that. And the idea is that we're not really wasting our time with sort of these kind of paths that have gone off in the wrong direction and keep calculating weight and multiplying tiny, tiny weights onto each other that don't really make any sense. But rather that we focus our computational efforts on the promising paths. Promising in this means that they have a high weight, which means they're sort of in areas where we think the true state might be. So what's the algorithm? But that's the only difference to sequential effective sampling algorithm is here, really. So at the beginning of every time step, we're resampling. So we're sampling indices according to the weight, and then we only carry on with the indices that we sample. So we might multiply or duplicate some particles, and we might discard some particles. And what we can also see is that we're getting out of our state inference, the sort of different equations that I showed, we're getting a few different densities out. So for example, here at this, so once we sample, we're propagating forward, and then that's kind of our prediction density, so we were interested in that. And then because we sampled with the weight, we don't really need to carry on. So what's changed here is that we don't multiply with the old weight anymore. We can forget about this weight once we've multiplied from it. So the basic rule is either we have to keep multiplying weights or we have to sample according to this weight, but not both, because then we would use them twice. So the idea here is the same kind of picture, that we start with the same, we're initializing, we're propagating forward, we're weighing, and now we have this new resampling step. So we're resampling according to sort of how big these dots are. And some of them will get discarded, and some of them will get multiplied. And then we propagate these forward, and because it's random, they don't all land in the same spot, but sort of start dispersing again.
Sorry, when you say multiply,
yes.
Do you mean you just add a bit of noise on the axes, or you actually, it's the same repeated particle?
Yes, so at time here, in this case, at time 1, so we're at time 1 here, at time 1 it would be the exact same particle. And then once we go over to time 2, because the process is random, that will sort of, each of the particles we randomly sample independently from the others, so they're going to disperse then.
Right, okay.
Yeah. So like if we had an animal or something, and we think there's one location for the animal at time 1 is really likely, then we put 3 particles at that, or 3 simulated animals at that point, and then at the next time step they might still have run in 3 different directions.
So you're basically sampling the same. You're sampling the same regions. Basically, you try to stay in the same high region. But then, would you have the typical MCMC problem of not jumping around too much in the space? If you have a bimodal distribution, you'd completely miss.
Yes.
Something.
So.
Or would you still allow big jumps?
That sort of has something to do with what I choose for the proposal distribution.
Right.
So we're going to talk about this. So for now, the proposal distribution here is just the process density, but we can change that to be something else. So if we suspect we have sort of big jumps occasionally, we can cover that. But on the other hand, if we think that we have big jumps anyway, then our model should reflect that, and then actually the process density should allow those big jumps occasionally.
Does it happen in ecology? I have no idea. I know it happens in like biological networks and things like that, but I don't know in ecology. I'm assuming because population is quite a stable thing, right?
Yeah.
You don't get big jumps. But I don't know. I don't work in ecology.
I'm not sure, but I think it doesn't really match up, because you have if you have enough particles at least, they should be able to sort of catch that. But then it becomes sort of a computational problem. So if you don't have enough particles, they might miss sort of an interesting region. But if you have enough, they should also go everywhere that's interesting. So if we look at the toy example again, the same kind of picture as before, and we can see so that the lines stay sort of thick until the end, and we sort of have a nice sample up until the end, and our weights are distributed nicely as well. And what we can sort of see here is that some of the paths are cut off, and then you can also see a little bit that some of the paths start sort of dispersing. So one path arrives, and then several keep going. Because we're not interested in this bit, because we know it's very, very unlikely given the observation we made, so we don't really want to look at that. Okay. So what sort of are there some nice properties of why we should be using this? So there's in fact a central limb theorem for the particle filter, which looks really not very nice. But so the one thing I just want to look at is this, the variance. And if we look at this sort of on fast that it looks like this might grow because it's a sum that goes until t, and the higher we make t, the sum we get. But actually, if we look at this integral, so this is very often bounded. So this is not always bounded, but very often in very many cases in the application, this is bounded. And then this. So this is the expected value if we knew sort of the case value that's above a while back, and this is the expected value just knowing the observation. And because usually the stuff that happened sort of 20 time points ago isn't so important, that doesn't matter. So this difference gets really, really small for a case sort of far enough away from t. And what we need is, for example, if we have exponential forgetting properties, if this the integral of this decreases exponentially, then we're fine. And we also, we need this bounded as well. And then we can bound the variance, and actually it's stable even if we run it forever. So the variance doesn't increase indefinitely. And I've looked at this in the toy example as well. So this is the variance of so I've just estimated the mean at every time point for sequential importance sampling and also for the bootstrap filter. We can see that sort of the variance goes up massively for sequential importance sampling, but it just stays quite low for the bootstrap filter. Okay. Can we make this better? This is sort of the basic algorithm. So like, I think, you already asked, can we have sort of a better proposal distribution instead of just proposing forward according to the process density? Can we use something else? Or can we maybe also use a better weight? Because currently we just weigh with this, but so something we can resample with that's maybe cleverer, that we don't just sample according to this weight, but something that might make more sense. And of course everything while we're still sort of having a filter that fulfills all the things we wanted to fulfill, like unbiased. And yes, we can. So that's called the auxiliary particle filter. And what we're doing here, so what's changed is in green. So we're now just with resampling indices according to whatever we want, really. We set weights to something that we like. And we also, our proposal distribution, we can also choose that however we like. And then we can see that here in the weights we're making up for that. So we're kind of so this, if we set the weights back to what they were, and this proposal distribution back to what we were, actually everything just reduces, and we're back to the bootstrap particle filter. But because it's not, we kind of have to have this rather complicated term that just sort of makes up for the fact that we sampled slightly from the slightly wrong weight, and we went forward with the slightly wrong distribution. So I think the big question is how can we, what can we choose here and here that actually makes this better? So something we would like to have that we sort of touched upon in the sequential importance sampling is that we'd like the weight to be sort of roughly the same. It's not good if there's a high variance, because a high variance in weight means a low effective sample size, or in the extreme case from before, sample size 1. So that's sort of a question we can ask is, can we choose the resampling weight and the proposal distribution such that our weights are all the same size? So if we look at this, we kind of want to choose this somehow that this is cancelled, and we get 1, or everything is all up to proportionality. So actually, so we can choose, if we choose this and this, everything cancels out and we just get a 1. So if we knew this distribution, so how is xt distributed given the previous state and given the current observation, and we also knew this, then we could get the perfect particle filter, and that's called the fully adapted particle filter. And this is, I mean, you can imagine that that's not always possible, but it is actually possible in some circumstances. For example, in the type problem, probably chosen. So this is the difference. It's the same plot as before. So we're looking at the variance of the mean estimate. We can see that the fully adapted particle filter just has a slightly lower variance and doesn't have these sort of extreme things that happen. And what I think is going on here is that the observation is sort of a bit further away than it normally is, and that sort of trips the bootstrap filter up because it doesn't look at the next observation when it projects forward, whereas the fully adapted particle filter here takes the new observation into account. So if the observation is a bit further away, it can handle that. So that's usually not possible. What can we do otherwise? So it would be good, so the general aim we can have is to sort of be close to this. For example, if we can do a Kalman filter update, we can, like a local linearization thing. And yeah, so that's nice algorithms where we use the uncentered or the extended Kalman filter for that proposal step. Which aren't the perfect distribution, but at least they can kind of take the new observation into account. And then for the resampling weight, there's lots of stuff we can do. So if we, for example, just don't resample, if we just set all of them constant to 1, it's really similar to sequential importance sampling. We don't really work with any resampling. What we can do, for example, we can look at, for each of the particles, we can look at what the expected value would be if we project it forward, and then say how close is the expected value to our observation, and then give it a really high weight if that matches really well, and give it a low weight if the expected value already doesn't match. And then another trick is sort of flattening the weight. So sometimes, as you said, like if we have big jumps or something, we might want to allow the particle to sort of deviate a little bit from where we think the promising region is, and not sort of punish it immediately by not resampling. So what we can do is we can just sort of flatten the weights and make everything a bit more similar artificially. And that means that sort of the particles on the side have a bit more of a chance, and maybe if we suspect that we might get some outliers or something like that.
You promised Rosemary there were no powers in this talk.
Huh? Oh, sorry. This is a power.
Is M an integer?
No.
But it's more than 1.
That's what I wondered.
Yeah.
Otherwise it
Yes,
wouldn't
not.
flatten.
Yeah.
I mean, we could also keep that it's all allowed. We could make it more peaky, but I don't think we would want it. Right. So what else can we do? So I've now pretended that we always resample multinomially, but that's actually the worst option. So we can do anything systematic or stratified. And then what I always do is residual sampling, resampling, so we're using the expected number of resamples. And then we resample only the little bit that's left. So expected number of, we calculate the expected number of samples for each weight, and then round down, and then just with the little bit that's left over, we do multinomials or something. And the important thing is that these three are sort of equivalent in the Monte Carlo error, and this one has the highest error, so we don't really want to do that.
Sorry, I
Yes.
lost the thread there. What do you mean by multinomial sampling?
Oh, sorry. Here, when we resample.
All right, once you know. Sorry.
Yeah.
Thanks.
Yeah. So whenever we resample, can we do this better than just multinomial? And yes, again, one of those three, whatever you like. And then the other thing, that's sort of a typical thing we might do, is we might change the resampling schedule. So in the bootstrap algorithm, we always resample at every time step. And then the important sampling is sort of the other extreme, where we just never resample and just multiply the weights at every time. But we can also do something in between. So we can decide we want to resample after every fifth time step or something like that, which has the same effect that we kind of give particles the chance to explore something that might be quite far away from where we think it's worth looking, and only then resample it after 5 steps. It's still not promising. And the other thing we might do is use the effective sample size, or an estimate of the effective sample size, which means we're going to look at how dispersed, what the variance of the weights are, and if the variance of the weight is very high, so the effective sample size is very low, then we resample. The typical value would be if our effective sample size is less than 50% of the actual sample size, or I think 80% is something that's been used in the literature quite a lot. Okay, so I think that's all the stuff for state inference. Oh no, sorry, last bit. So what if we're interested in the entire path, not just the last step, but the entire path? What we can do is we basically just run the particle filter, and we save all the particles along the way. And we, instead of just saving the current time point, we sort of remember where everything came from. And the problem is that we have this thing called path degeneracy. So if we look here at the sample at time 50, it looks really nice, there's lots of stuff going on. But then if we follow those paths backwards, we find out that actually from time to 32-ish, they all come from the exact same particle. And so if we now want to make inference about this time here or whatever, we just have one sample, really. So that's not very helpful if we want to know something about the entire path, or we want to know something about time 15, given all the observations. So there are a few solutions to this, and one that I really like is the forward filter backward simulator. So we're basically starting by running the bootstrap filter, and we're remembering all the weights and all the particles in between, and then we're going backwards. So we're taking the particles at the last time step, and then instead of, we might know that this came, then we go backwards, and then instead of following this path, definitely taking that as the ancestor, we're sampling from all of these options. And here we just happen to sample the one where it actually came from, because that might have felt quite likely. But yet now if we look at the next step, in the original particle filter, this came from this ancestor. But actually now we're resampling, and we can sort of take this backward path through the particles. So that's sort of the idea. We're going through backwards, and we're just, out of the entire particles that were available at some sort of previous time, we're choosing where that particle might have come from. And that then gives us a really nice full. So that means the paths are as dispersed as they are at the last time point, at the first time. Right. And then for next time, so how does all of this relate if we want to estimate parameters? We can actually use the particle filter to estimate the likelihood, and that's all we really need is the weight we calculate, nothing else. And that gives us a nice estimate of the likelihood, which we can then use for maximum likelihood estimation or to calculate the posterior in the Bayesian framework. And what I think is really surprising and nice about this is that this is actually an unbiased estimate, even though everything else with important sampling and the particle filter, all the states, that's always a biased estimate, but this likelihood estimate is actually unbiased. Pretty nice. Great. And then I just thought I'd give some sources for further reading. So I think all three of these are really nice introductory things. The first one is only on state inference, and the other two are both on state inference and also parameter inference. And yeah, they kind of show the introduction, but also I think this one is most sort of shows the most sophisticated techniques, and the first and the second are quite introductory. And that's it. Thank you.
Questions, clarifications?
Can I ask a very naive question? How do sequential Monte Carlo methods differ from hidden Markov models? Are hidden Markov models special case?
I think that's just a special case in that the underlying states are discrete and not continuous.
That's what I thought.
And I think because they're discrete, they then allow for other kinds of fitting methods that might be more efficient. But you could certainly apply all of this to a hidden Markov model as well.
Yeah. So a lot of these methods, I got the understanding the idea is you can always look ahead to see how well it matches the observation one step ahead. Mm-hmm. I'm thinking there might be paths that go into rubbish places for some observations but end up being brilliant later on, but you throw them away.
Yes.
So I take it that will there be methods that maybe simulate several steps ahead to try and...
Yeah, but that's kind of the idea. For example, here, if we just don't resample very often, if we might expect something like that happen,
right,
we could do something like that and just not resample. And then we could, or we could do something like the tempering of the weight, here, something like that we just don't chuck them away immediately and give them more of a chance.
Right.
And I think that just kind of depends on what your model looks like and what you expect.
Is there cases where the weight when they're resampled can be derived from how well it projects further into the future than just one step ahead?
Yeah, so I mean this is kind of the expected value thing. There's no reason why you shouldn't do that for many steps ahead. So you can basically, because it all fits in this algorithm, you can really choose whatever you want. So if you have a clever way of realizing that this particle might fit really well in 10 time steps, you can let that be reflected in this weight here, and then you just need to make up for it here.
So the problem with going a long way into the future is that it takes a lot of computer time, right? And so people don't tend to want to do it. But the case that I've seen where it was really important was somebody was working on 3D protein folding, and so you're basically taking this strand of protein and then you're folding it up into some 3D structure, because that's how proteins work, right? So that 3D structure is really important. And it's easy to, when you start folding it up, kind of box yourself in the corner and have it just obviously not going to work. And so rather than taking a very expensive look at it, they had a very rough look ahead to see whether it had enough space to basically work still. And we're using that as their, so it was a long look ahead, it was 60 steps ahead, but just kind of saying, oh, very rough, it looks like it's going to work. Yeah, right. And then we're using that as their auxiliary way. Well, they get talk about
follow on from Richard's question, these changes like the tempering, you have to make that decision to begin with, or that you could adapt to the value of M, say, as you go through?
I think you could adapt it, and I think you can even just decide while you're running it to adapt it. There's no...
And everything falls out the same, you don't...
Yeah, so as long as you make up for it, as long as you make up for it here, you can decide here, basically, what you're going to resample as. So you don't even have to decide before, you can just decide while the algorithm decides, as long as you make up for it.
Could you be running hot and cold kind of chains and have them speaking to each other?
Yeah, I think, yes. There's no reason why it should have to be the same throughout, and so,
That's a really good idea. I've never heard of anyone doing that before. So, but you could have half of your particles on one temperature scheme and another half on another, as long as you keep track of which is width.
Yeah.
So that would be like, I'm going to have m equals 1, so that these are going to be the ones that, I suspect should be the best. But I could have an m equals, let's say, 4 as a kind of, so that particles that are much more robust for outliers and stuff, but they're not likely to be helpful if everything goes smoothly. So yeah, good idea.
So one question which is maybe naive as well, but so in this case, because we know the parameters, I'm assuming there's no concept of burning in, right?
No.
No.
And we also want to start, I mean, that's not quite true. So we might sometimes not be so sure with R. Right, here. So sometimes we're not so sure about the initial PDF.
Right.
And then we would be quite careful with interpreting the first few things that come out of that. So that's quite often the case, that your initial density is sort of a bit hand wavy, and then after a few, because you like your process and you like your observation PDF, and then after sort of 10 or so, you're a bit more sure about what the particles will take you.
And yeah, the other question is more probably like what methods are available. So when I was looking into this method, we were looking at kind of like SAR type models, so following an infection chain.
Yeah.
And I think the issue that I came across, and then I ran out of time and funding and everything else, and the will to do it, was, so this was an example with TB in cows. So once you actually find someone who's reactive, you have to kill that cow, right? So then your dimensionality halfway through your chain changes. Because if you removed an individual from your it's not one individual, it'll probably be multiple individuals, and at different time step, and then you introduce people as well. So you introduce cows into the herd, and you're removing cows from the herd. Yeah, I've never got around and solving that problem, basically. I was wondering if there's any, what kind of techniques there are when dimensionality kind of changes.
Yeah, I mean, I'm wondering if you have sort of a model with, I don't know, suspected will infected discovered or something, and then you can just have that in your process that everyone who gets discovered is then killed in the next time step. I don't know. I would think that if you sort of have enough categories in your state vector, you could take account of that.
I was struggling to understand why that might be a problem in the first place, because each particle is like a simulation of the world, and it can have anything you want in it. So in our seal example, there are animals being born all the way through that, and animals dying. So that's not really a dimension change. That's, so I'm not sure why it would be a problem at all. Like what was it that's causing the problem?
I guess it was a bit different, because every particle was a simulation of the infection process.
In an individual animal, or
in a herd?
In a herd.
In a herd.
Okay, but that herd could vary in time.
Yeah.
Sorry, not vary in time, vary in size, couldn't it? And through time.
Yeah.
That's how I set it up. So in the same way that, in our case, a particle is a seal population where animals can be born and die within that. This one could be a herd where animals can be discovered and also new animals can be removed. And each particle then is completely different depending on the stochastic, simulations that you're performing. But there's no reason why they can't base for animals in them, I don't think.
No, that's I'll dig it up again now that I know that there are experts here. When you're on maternity leave?
April. Months ago. Yeah.
Okay. Can I just ask a silly question, maybe? So if you're not interested in, say, quick real-time prediction or anything like that, could you just implement a standard MCMC to get your posterior distribution, or it wouldn't work really? Like a metropolis case, some standard metropolis case.
You mean for the states or for the parameters?
Not for the parameters, even it's just for the states. Even.
So I think you can, but the problem is designing a good proposal distribution. Because so that's usually the tricky part. So if you have a good way to have a good proposal distribution, and then there is a way you can't just. But you basically need to. I mean, you need to resample the entire path, and that needs to be a path that kind of makes sense given the observations and the process. So that's the tricky problem. And if that's easy to do, then MCMC works.
I think it's exactly right. So these problems. I mean, sometimes it works just to do something standard, but you might say, okay, I'm not going to do a whole path. I'm just going to break it down and propose one new state at a time. Right? I've got this underlying state. I'm going to move it. But if you're halfway through your time series and you propose a new state, then that could make the subsequent value that you have for the next time period very unlikely. And so those proposals always get rejected. And so that makes it a very stiff problem. And so you're now proposing tiny little moves, just to keep it from you, and then you don't get anywhere. So it mixes really, really slowly. So Fanny's right that you need a clever way to propose a whole new path that's kind of not going to get rejected.
Yeah.
That's the trick.
Yes. Because you cannot use the full the Markovian conditioning.
Well, so
it doesn't become easier, kind of, because of that.
So we had a PhD student, John Bishop, who worked on can you come up with a smart proposal that uses the future conditioning as well as the previous conditioning, and so come up with something that's just jointly across both those two. But it proved to be for anything other than toy problem really, really tricky. It just took a lot of time to then actually work it out. That was defeating the whole purpose. I mean, it took a lot of computer time to work it out because there was a lot of different options.
That's one more. Sorry. Is there anything wrong with using multiple? You're all assuming the particles are all independent when you're making the proposal. Is there any problem with using information from other particles to propose the next one? Like you could look at what the best particles are doing and get closer to them without resampling completely and throwing away bad ones. Does that make sense?
Yeah. I think that would be fine. I'm thinking if that's something that some people are doing or not.
Isn't that what you're doing already, right? Because you're sampling from the high.
Yeah,
high
so
region of
you're
probability and
already
deciding
getting into the promising regions by that. So what you could do, I think I might have seen that somewhere, is that you basically you're approximating your sample at certain times with a normal distribution, and then you're saying let's just sample from that normal distribution now. But it doesn't really help you a lot because you're losing information that you might otherwise have had. Yes, I'm not sure.
Are you talking about at the resampling stage or the proposal stage?
I'm talking about at the proposal stage.
Yeah.
The sense that you're resampling throws away those, you kind of lose the diversity of your sample. Whereas if you just kept them but proposed towards the better samples, you keep all your samples as you go.
Yeah.
That's my thinking.
Yeah, I think it's totally fine as long as you take account of it in your ways.
Yeah. And I think something that is actually an algorithm that I've seen is that you instead of just resampling, I think this is similar to what you were asking, instead of just resampling and having an exact copy of the particle, you sort of do a tiny little normal distribution around that or something and then sample from that. And as long as you keep account of that, that's fine. Yeah, I don't know if it's really worth doing because the randomness comes anyway.
But if they're too far away, right, to go back into the right region, then you'd have to enable a really big jump for those particles, right?
Yeah, but the going back into the right region happens through the resampling.
Yeah.
So it doesn't need to happen through the proposal.
I'm assuming you don't compute an R hat, right, in this case, because you've got enough particles to start with. So in standard MCMC we compute an R hat value just to make sure that all the chains end up in the same place. I guess in this case you're implicitly doing that through the particles, so you don't have the same. So in sequential Monte Carlo, what do you use as a measure of convergence then? I guess it's next week, right? Because it only makes sense when you're comparing the parameters rather than in this case. Assuming the parameters.
Yeah. I mean, I think a measure of it is looking at the weights, and if you sort of resampling at every time step, you're just resampling one particle n times, then it's not really working. So I think looking at how the weights develop over time is sort of a good diagnostic tool.
Convergence isn't the right way to think about it, because in an MTMC sampler, you set up a sampling regime so it converges to some stationary distribution, and you have to wait for that to happen. Here, you start off in the stationary distribution at the first time point, because that's what you're sampling from, so you're bang on to start with, right? So what's happening, what you're looking for is divergence rather than convergence, right? When the weights start collapsing, then you diverge, but up until then, you're getting samples from the posterior at each time point automatically. So there's no concept of convergence, you're already there.
But it's a function of your parameters, right? Now, if you don't know what your parameter is and you're estimating them on the way.
No, if we had unknown parameters, we could propose from the prior distribution of the parameters of the first time period, and from some prior distribution of the states at time naught. And okay, that's a perfectly valid sample from a prior, right? And then we would project forward one step, and do some stuff that Fanny's going to talk about next time, and we get a perfectly valid estimate of the posterior after introducing the first data point, parameters and the states. And as long as things don't go wrong, it's going to be perfectly valid every single time. And then when you get to the end, it's a perfectly valid distribution from the entire posterior. It's just that things might have gone wrong along the way, like you might have lost a bunch of particles, in which case you diverge. So as long as things don't go wrong, there's no convergence. You're there from the get-go, which is the wonder of this thing, really.
I guess other than that it's biased a little bit and only asymptotically unbiased.
Yes.
But I think everything is asymptotically unbiased, right?
Okay, time's up. If you have more questions for Fanny, please corner her. And I think it probably also be really helpful for people to put the slides up somewhere, just maybe we could email around to the seminars just saying where they are so they can make that. And then part 2's in a couple of weeks. And next week, who's talking next week?
Somebody from Duke who's visiting Edinburgh, I forgot her name, she's talking about data science education.
Oh, okay. Thank you, Eric.
Yeah, Mina something.
Okay.
It's like a Romanian name. Talking about data science, yeah.
She's part of our studio craft.
Fabulous. See you there. Thanks, Chris. Oh, and the random.
Thank you. That was one of the clearest talks on suggestion.
I started taking notes.
I've seen this, what I've seen people do is use substance descriptors. That's quite a standard thing to do. Put them in square brackets like that, just to indicate that that's a particle and not a sound.
Oh, okay, yeah, that was so was that really cos of x squared, did you put the brackets?
Yeah. I think,
Or it
yeah,
could be
really
cross squared of x.
Indeed.
Okay.
I haven't seen that example before. I think it's a nice example either way because it's very jumpy. Not jumpy is the wrong word, sorry, but it's very demanding. There isn't an easy pattern.
I'm not going to be annoying you, so don't worry.
Really, like if you have, I mean, I think if it's something that's nice, I definitely, I'm not going to look for mistakes.
Like I said
Yes.
Yeah, it was like.
Yeah, well, that's exactly. Series of people who are really interested.
Because I just see people from
No, I didn't know that.
Because I remember looking at things like reversible jump and things.
I suppose there's no interaction that makes sense.
It's really weird in research, like even something that you done 2 years ago, like, how can I forget that?
I got a question the other day about something I looked at half a year ago. I know it doesn't work, but why?
It's really frustrating. Like, I'm finding this as well, like when I'm writing this poetry, it's just like, I've done this 2 years ago, why can't I just remember this? Why is it so hard to remember?
Getting a question about something that you did a year ago and not remembering why it didn't work, that's called a viva. That's going to
Given that it's only yes, I agree.
I think it's just old age. Like, tend to like forget everything. I think once you read the threshold of MCMC paper, like they all merge into one, and you're like, yeah, okay. And some papers are just so. I find them so inaccessible. Like,
yeah, there are different people have different backgrounds in writing them, right? So you get some highly theoretical MCMC and particle filtering. Actually, some of the paper, the unbiasedness paper.
So is this online?
For example, it's like it's absolutely epic.
I really tried.
Yeah, it's absolutely epic.
and sometimes it's like simple concepts, right? And they still make it really hard to understand.
Well,
I find Michael Betancourt is really good at writing. He writes a lot of archive papers where he explains things. He's a physicist, but he's got an engineering background. So, I mean, of course, he writes a lot of maths, but he's always like from the easy side. Like he approaches it like you're an idiot, and I really like those papers. And Mark Girolamo is quite good as well. If you've ever been to any of his talks, we should really bring. I don't know what the situation with money and bringing his own.
Well, usually there's no problem. So this year we're tight for money, but usually there's no problem. So you should. And Balance is always looking for suggestions for stats speakers, so you should suggest him.
Yeah.
So we don't suggest people, we get all these econometrics ones, but the balancing ones, right? All his friends, right, which is also fine, but you know, it's not. So yeah, no, if you've got something to suggest, absolutely. And also, especially people like that, it might be better to book them at, you know, many months in advance anyway, and just say, would you mind coming next year? You know,
yeah,
more
he's a very busy person.
So people tend to say yes if it's better in the future, right? Yeah.
So yeah, he's Scottish. And he's got this, I don't know, Scottish way of like.
But he's not in Scotland now, is he?
No, he's Warwick.
Warwick, yeah.
I think he's in Warwick, yeah. And yeah, I know quite a few people who are using these methods in infectious disease modeling. So if you're interested in that, I can invite.
Yeah, that'd be fun. Sure.
People like that. Yeah, I'll make a list and.
Yeah. Send it on to Balance, yeah. You should dig out your effort now. We can get Fanny to tell you how to do it right. She's an expert now.
Yeah.
But I thought that was I really enjoyed that course in Uppsala because they were doing it from such a different perspective, like the kind of problems they were looking at with all this object tracking and like how do you track a drone and how do you do like visual effects now, maybe movies as well, like someone's wearing a tracksuit suit, how do you stuff like that, which I thought was so cool, and that just kind of had the effect they method.
So the person who got me into this originally, his application was that his wife was an opera singer, and he was interested in old records, and he wanted to get scratches out of the records. So what was the real music underneath that noisy signal? So it's literally a noisy signal.
That's pretty cool. I always find that an application can make you learn. So I remember when I was learning random forests, the application that really got me into it, and really got me to understand random forests, was the kinetic. So this was about 7 years ago when Microsoft wrote a whole technical report on how they use random forests to identify different parts of the bodies in front of the kinetic, the Xbox. It was brilliant. It's really, really nicely written. I think the guy's called, his surname is like Christianini or something like that. It's a very good technical report from Microsoft if you want to.
That can be one of those things where they find, like, they market it, they test it, they market it, they produce it, and then they find it doesn't work for black people. Because it's designed to, like, find your white hands or something like that. You know, they just make some enormous screw up. And
have you ever seen the Google Photo screw up?
Yeah, where they put chimp on black guys, didn't they?
Gorilla.
Gorilla. Yeah. It's just like, oh my god.
Don't work in machine learning.
No.
Alright, cool. Well done again. Looking forward to the next one.
Cool.
Your talk gave me an idea. I have no idea how promising it's going to be yet. And so obviously, we want to bang in as many particles as we like. But I was thinking on the GPU, the resampling stage is what really fucks us up, because that's really expensive, because we obviously need access to all this value. If we run threads in a block, so basically just particles where the calculation is going to be happening on the same group of cores on the GPU, they have a 64 kilobyte register of shared memory. So basically, we could have resampling in a way that doesn't make the parallelization
local
horrible with that. And so if we then run, say, X thousand copies of our particle filter, where each particle filter only has around 16,000 particles, because that's how many floats you can fit in a 64 kilobyte register. If we then have our final estimate be like a weighted sum of however many individual 16,000 particle filters we had.
So you're basically like keeping a weight for each of the bundles?
Well, so I don't know how you would keep a weight for a bundle of them, but basically could we break our however many...
what you're doing now.
That's what I was going to say, is I'm kind of doing that, but on a much, well, less efficient, but on a bigger scale. So I run 1 million particles at a time.
Okay.
And then run 100 or 1,000 of those. So this is a mini version of that, basically.
Yeah, this would be a mini version of that, but the cool thing about it is that because the GPU I'm working on now only has 9 streaming multiprocessors, so we could have like 9 lots of these particle filters running at once. But if we had even a little bit of server time on one that has like 20 GPUs, that's 20 lots of these running at any given point in time, anytime you do this.
And the other really big advantage of that is that those don't interact with each other until the end, necessarily. I mean, they might not, they might not, and so it gives you an accurate estimate of the Monte Carlo error, which is very hard to get otherwise, because if all your particles have been interacting with each other all the time, you're really not sure what you end up with.
There's so much overlap in the behavior.
And that's why, that was the first reason why I started doing them in batches. So, because I say I did them in batches of 1 million, but I could have done fewer batches of 10 million or more batches of 1,000, right? And so I just ended up mucking around with it and working out that that was a good compromise for me. But my main motivation was, I'll just run it a few times and see, you know, what the Monte Carlo error is, and then just average across it to, you know, to.
So that might be something to focus on as a chapter then. Looking at that trade-off.
Yeah.
Because what you gain, what you lose in particles, you gain in being able to run them at the same time, and it would be interesting to see like where do you need your hardware to be at for that trade-off to actually start making sense.
So the only thing you're saying you need to share is the index, right? You don't need
the
to
weights,
share, the weights. So that's why it's one value.
It's because everything else can just happen independently, right? I don't care about the population size of another particle to project forwards.
But when you resample, don't you then have to copy that across into the new place?
Copy what across?
So when you resample your particles, so you've got these shared weights, but you're going to be resampling, aren't you, within this set? And but the resampling step involves copying what the particles' values are across the new one. But that's relatively fast, is it?
That's okay, so my figure of 16,000 particles would have to go down, because obviously we need to keep some of that memory for the actual values that we're copying.
So that would have to be shared too,
So that would have to be shared, which would put an upper limit on the number of particles we could have running in one of these independent systems of groups of particles. But that's completely fine.
So what you're saying is those groups of 16,000 would not communicate with any other group of
16,000, that's right.
But within they would work like a standard...
Yeah, and
like
it would
work like a standard particle filter, or okay,
exactly. It would work exactly like a standard particle filter.
But it might be that you want to, you could have more particles if they shared less, so you can think about some things that they don't need to share, perhaps.
Yeah.
So, for example, sometimes right now we save the entire stream because hey, this is like all 3 of you in one room. There we go, share the moment. So we want to save the whole trajectory sometimes, so we save all the past states, but in some other applications you just don't need that, you only need to save the current state. Just as an example. Because otherwise the longer your time series, the less particles you can be allowed.
I mean, for everything that's parameter inference, we don't need to save the paths at all. We don't have, which is good,
Yeah.
so we can just check them.
Yeah, we just want to get to the end and work out what the likelihood
Yeah.
is, right? So.
Especially with the hardware we're working with at the moment, the big upper limit is mostly just memory.
Right.
Because the GPU has 3 gigs of RAM, which is about 700 million floats. 700 million floats when it takes like 10 floats to simulate a binomial is not very good. It's not that many particles that can be running independently. And then when you think that at any given point in time you don't have 3 gigs of memory, what you've got access to quickly in cache is orders of magnitude smaller, and it just becomes a lot less interesting unless you've got a 2,000 pound graphics card. Which
you may get one day if you're good.
if we get some promising results.
There we go.
But the server time is significantly cheaper than that, which is good,
Right.
because we can toy around with a lot of different versions of algorithms on server time before we actually decide what hardware makes the most sense for the types of algorithms that end up being the most promising.
Yeah.
And I met a few people at the 2-day GPU game I did in Edinburgh that deals with Cirrus, the Cirrus cluster, and then the new version of Archer, and so we might be able to get some free server time with academics on that, at least for long enough to do some pilot stuff.
We should be able to actually, shouldn't we?
Yeah.
There's no reason why not, right?
Yeah.
So it's supposed to be a share.
And I'm sure even CS has, like they might not have thousands of GPUs, but they've probably got at least a couple of beefy ones we can use for a few hours a week to run and stuff. Yeah.
Cool.
Right now I've done the C++ version of the file you sent me, and the R is actually pretty good at sampling from stuff, so the C++ samplers are slower, and so...
I can code efficiently. That's what I hear from that.
Yeah, and so basically I need to find faster samplers, because I'm not going to bother putting it on GPU until I've got the C version.
Yeah, the C version is...
You can take them right out of R, right? So the R code is open source.
I looked at that, and I'd have to hack it quite a lot. Because there's...
But that's what my C code is. You know, when I was looking at the random number generator, I just hacked them right out of R. So because there is a lot of overhead on that. It's all these error checking stuff and all that stuff. That's like, but yeah, ultimately you just get to the algorithm and just put it out. So
I think I'm going to end up doing that because the inbox stuff.
Right.
Yeah.
Not surprised.
Yeah. The big problem, binomials are really annoying to sample from, just because in the particle filter, obviously, your n depends on the state.
Yeah.
Right.
Yeah.
And so you can't pre-generate a bunch of them in advance.
No.
And so one thing that would actually help us save a lot of computation time is figuring out if we can use normal approximations or anything like that, just so that we can pre-compute the random component on a big batch, well, as a big batch on the GPU already, with the CUDA libraries for random number generation that are already there. And then finding a clever way of doing coalesced memory reads for them is going to be a lot faster than generating them as we go, as we really memory. I think. But like in this seal application, the n is like usually above 1,000.
Yeah.
And so unless the probability is stupidly low, normal approximations are probably going to be rough, kind of smaller than the simulation error anyway.
Right.
So we could maybe get away with that, because then all we have to do is simulate a bunch of uniforms, which is super fast, and you can easily do a batch and then do like an inverse.
Felix, did you emailed me about having a PhD meeting, didn't you?
At some point later this week or maybe next week?
Yes. Why don't we just sort it out now if you want to?
Okay.
Oh, no worries. That was just me rambling.
No, he was talking about uniform fast simulation approaches, which is not rambling. Monday, after coffee.
Ooh, Monday, yeah.
That work?
Monday 17th.
Monday is the 17th, indeed.
Oh, it actually works.
Okay, cool. Are you guys all tutoring to help?
Yeah.
How many are you doing?
I've got 3 groups,
Well,
plus
that's not
2
terrible.
hours a week of first year maple stuff.
Yeah. Actually, quite nice. I have 3 example classes and 1 tutor group. Example classes are lovely.
Have you had your tutorial?
Yeah, this morning.
How was it?
Yeah, nice. Super easy. Yeah, that went super smooth. Like my smoothest so far. And it was the one where Victor was watching. So I was like,
Oh, so are you watching each other? Like,
yeah,
we actually
basically we've just done it in a triangle.
in a triangle, so we're like
It felt
triangulating.
easy because we were all doing different modules.
Yeah. So you're sharing tips about how to get students to like come out of their shells a little bit.
Yeah, I don't know what it is about this second year stat module, but they really don't like talking. In linear maths that I was tutoring this semester, they're kind of better about speaking up.
Yeah, but I
But
feel
in
like
stats, it's just
Really? Wow.
yeah.
But yeah, I've noticed as well when you do like sort of when you do more mathematical, more programming modules in my undergrad, always everyone's super engaging. Second we hit a stats module, even with those same.
But it's weird because in honours at the time, it's literally just the second year
Is it
module.
confidence maybe? It's just totally new material to them.
Yeah.
They don't know what to say. They've never encountered it before. They're like,
I think so. It's gotta be. I don't know if it plays a big role, but a lot of the tutorials for this specific second year stats module are in 1B, which is like one long
oh yeah.
room.
Is that the one that's by the place where
Yeah,
there's coffee?
yeah. And I think that makes it hard because you're just in this one big row, and it's just a weird layout, and you can't actually see many of the people that are around you unless you like lean forwards.
Oh yeah, so they can't see each other yet,
Yeah.
because you can see them
Yeah.
quite clearly, right?
Yeah, exactly.
They're along and then they curve round at the end, in my experience. And I'm like
Yeah.
And
there.
I
and
always
the
feel I
screen's
don't
there.
understand how anyone sees what I'm writing on the board on that.
Yeah,
Especially the people
The
that
people
are
on,
like.
on the edge of like, can you see that? Like, yeah, you just don't care, do you?
Yeah.
But I think, I might try to request a different. I think it's
That
also
one.
very, very bad because you always have to look around all the time. You can never see all the students in one go.
Yeah.
It's funny because that's the only room I've ever tutored in.
Oh, really?
Totally used to it.
It's the same as 1C. It's just shit.
Well, they used to be
Oh yeah, 1C.
1C is also it's like downstairs.
Yeah,
It's just,
yeah.
So it used to be a corridor. So all that lot was a corridor originally. So,
because
But I used to have like, I had a group at 9 and then one at 10, and the one at 9 they just never said anything, and the ones at 10 like they were discussing, they were all
woken up by
like,
then.
I don't know, it was
Yeah.
like a whole different world. It was, I mean, I didn't really do anything different.
Yeah, my second group is for that day is 4 to 5, and they're all just completely
They're done.
dead. Yeah.
I used to go down to Fisherman's Arms and buy pastries and give them out. I started by giving them out for people who would get up on the board and do things.
Yeah.
And that works pretty well. Although some of them don't actually want food, right? 'Cause
Right.
they're trying to not eat so much or whatever. But then I would give it out for the most outlandishly wrong thing that somebody would say in order to try and encourage them just to say stuff.
Even if I
Yeah,
like
even if
that
it's
a lot
wrong,
actually.
so-
That's a really good
Yeah.
approach.
Well, actually,
But
when I
you just
started,
get like 11 people who just shout like.
that's fine. They will get a cake then. That's totally fine. And then everybody's having a laugh, right? So that's fine.
And
Yeah.
they're doing something.
Having a laugh during a statistics tutorial is definitely an achievement.
Yeah, exactly. Well, I used to give out booze originally, but I got told that wasn't appropriate. So just bring in a six-pack and give out beer.
Could one get in a lot of trouble? For
Yeah,
doing that?
exactly. That was like, no, you're not doing that.
And good old days.
That's a shame.
That's back in the days when you could also still hit them when you didn't when they did something you didn't like.
I'm not that old. And anyway, what do you say? You can't hit them now? What?
No one told me.
Oops.
But I love that the giving cake. I think that the cream cake as well. Like sometimes people bring cakes and like their papers get rejected and stuff.
Right.
Like, it's
Yeah.
such a good thing because you always think you're the only one who's like.
Yeah, we're gonna go to the bar and drink because to celebrate the rejection of my papers.
Yeah, but I think it's good to make that a bit more. It's not horrible. It happens, and it's
Well, you learn probably more.
Failure is an
from those.
option.
Yeah, failure is an option, and it happens all the time if you try enough things. So-
Just resample from the past.
There you go. So Tiago kept a track of, because I wasn't his official PhD supervisor, but I interacted with him on his PhD. He kept track of what proportion of my ideas were good ideas. 1 in 20.
1 in
1 in
20.
20 was a good idea. Like a really good idea. So 19 out of 20. They're either meh or they're like bad. So
That's a good thing to keep in mind next.
yeah, you guys should definitely bear that in mind.
Next meeting. It's just about 5% of the time if I listen.
So you
I
need,
might just
no. You need to become skilled at filtering out the bad ideas quickly. So you don't waste too much of your time. That's the main skill.
Okay. I'll keep that in mind.
Good training.
But failure is definitely an option, right? You just like, oh, that was. Then after a while, you think about it more. And you go, oh, actually, it was a really bad idea.
Yeah. All right. So
Thank you for that, Fanny. That was great.
Yeah, that was wonderful.
Rosemary's struggling with your notation, so.
it was lovely. It's like the mathematics versus statistician
God.
class, right?
I tried. I really tried, but it didn't. Tell about it. I also use capital X's and not, I mean, I use small X's all throughout and not capital.
Oh, you used a capital X at one point, I noticed.
Yeah, but then I stopped.
Oh,
Like
then
on
you
one
stopped,
side,
okay.
it's like, this is going to be painful, won't it? I'll just stop.
Well, I did think if we do something like this ever again, I would maybe we should just turn it into quite a long series of like like not a reading group, but like a class thing, because that could have easily taken 3 lectures, right? If you really want to explain it,
I mean, it was
so
half
everybody
of
understands
that workshop that was for PhD students who were already into that topic.
Yeah.
And that took a week, and it was half of that week in one talk,
in one
basically.
45-minute talk or whatever. So yeah, so we could take a lot more time with it, right? So. Well, I think for people who knew something about it, they learned a lot, and for people who knew nothing about it, they got the idea.
Yeah.
That's the main,
Okay,
you know.
that's good. Yeah, I was
Yeah.
really struggling a lot with, where to aim it, basically. And I also don't really know like, how much people know this stuff.
Yeah.
What sort of, like, important sampling, I kind of think probably, I think everyone, because I do that in my sleep now,
Right.
I think everyone else does it in their sleep, but then I realized maybe not.
Well, it's part of the undergraduate curriculum, so every undergraduate will get taught.
It's in the base
something.
model, isn't it?
Yeah, it's in the base model,
Yeah, I realized when you explained it that
Yeah.
a bit covered.
Yeah.
But briefly, for some people.
But even then, like, it's not something that everyone does in their sleep. Because I had a conversation with Andy the other day, and he kind of asked me about that. Obviously, it's like that. And he was like, oh, yeah, right. Yeah.
These things are really hard. I mean, it's a very hard thing to know, to be in somebody else's skin, because things that we do all the time we find really, really easy, and other people find, I mean, just teaching programming to beginning students, they can't get their head around the for loop. Like, how's that I thing varying all the time? Like, what value has it got? And they just can't, but once they get it, it's like, oh yeah, to us it's totally second nature, right?
A first year asked me, I think it was on Monday, I used the Windows key to like open up a menu so that I could search to open Maple. And the student was like, is that the Maple key? Do I need to press that to run the Maple code? The Windows key, really? You don't know the Windows key?
No, I'm actually not surprised. So a lot of the maths students don't like computers at all. They'd be much happier with a pen and paper.
Right.
So, And
I was like that, I think, until like way into my master's degree.
We're actually having a review of the computing provision at honours level. Or actually, no, all the way through the degree. It's starting and it's going to carry on for the rest of the semester now because there's been so many students complaining about not 413, but the other 2 modules. They really don't.
Oh, how bad the teaching is.
No, just that it doesn't meet their needs. It doesn't.
Right.
It's not what they want. It's so. Yeah. It's just so we're going to review it. And I think we should review computing stats as well and just see how we can change things. So the big problem on computing stats is the master students and the undergraduates in the same class because they come at it with vastly different amounts of experience.
Yeah.
So.
And weirdly, it seems. I mean, when I was doing the module, it seems like the undergrads actually end up being more familiar with it.
Yeah, well, they've already met R, right, by the beginning of it, so there's this quick refresher, but they already know that stuff, and the master students are like, holy shit, I can see that mountain looks like this from here.
I mean, some of them are like come from a computer science background, and they are then again super fast and know everything.
Yeah, they're coding in RCPP from like the third year.
Yeah.
But then others have never coded a single line in their life.
But in general, if you look at the distribution of marks, so on that first assignment, the master students are way worse, and then they kind of catch up.
That's cool.
So they're on because they work harder, right? They're just on this kind of accelerating trajectory. But the last year I taught it, they didn't catch up by the end. So they were still getting worse marks on average than the undergrads, and that made me think it might be better to split it. Eric was always suggesting that as well. He found it very difficult to teach them because he could see them like really struggling. Yeah. Anyway.
When are we meeting?
I don't know. I was going to ask you the same question. Well, I could ask you the same question too, Phil.
Yes, I was thinking that.
When are we meeting?